Hello and welcome everyone to the new episode of the AI co-learning program. I'm your host Bruce, and it's great to have you all with us again. Today we're diving into one of the most exciting frontiers in AI research: foundation agents. So, as AI systems evolve from large language models to agents capable of reasoning, memory, and self-reflection, we're witnessing the early construction of what might be called cognitive engine, the underlying architecture that empowers agents to plan, adapt, and interact with the real world. So today we're truly honored to have with us Dr. Bang Liu, the associate professor at University of Montreal, whose research focuses on AI for science, natural language processing, and Gen AI. Today he's going to share his insights on advances and challenges in foundation agents. So hi, Dr. Liu. Thank you for joining the co-learning series. Now the floor is all yours.
Thank you, Bruce, for the introduction. So I'll start sharing my screen.
Okay.
So can everyone see my screen now?
Yeah, I think it's cool.
Can you see the slides in full screen mode?
Yes.
Okay, yeah. Thank you everyone for attending this talk. So I'll talk about advances and challenges in foundation agents, which is based on our recent large-scale survey about AI agents. So I will mainly start from introduction to the concept of foundation agents, which is a general framework to describe what exactly is the cognitive process of an AI agent. Then we will mainly introduce two recent research in our group. One is about the reasoning system, and another is about the memory system. And lastly, I will go very quickly to briefly mention the application of applying AI agents to material science. So I won't cover every slide in detail here, but I will just give you some impression. So if you check this, the different entities here, like robot welcome, human, self-driving car, camera, health tracker, and so on. So if I ask you which of these are agents, then you need to think about what exactly is the definition of an agent, right? And if you check the very classical AI textbook, which is from Stuart Russell and Peter Novin's Artificial Intelligence, a Modern Approach, it defines that an agent is anything that can be viewed as perceiving its environment through sensors and acting upon the environment through actuators. So this is quite intuitive, like you have some sensors to get signals from the external world. And you went through some cognitive process and making decisions about what actions to take. Then the actuators will transform the actions to the executable action to the environment, and the environment will update its state. Then you will get the new observation, and you do this again and again. So I basically asked ChatGPT about the question asked, which of those entities are agents, and it gives this list. And you can see that the robot welcome, human, AI chatbot, thermostat. You can see even the thermostat is a very minimal agent because it matches with the definition. And for camera, it has sense only but no actions, so it's not an agent. Similarly, plant, software, and so on, they have no sensors or actuators unless embedded in a system. So this is how we define what is an agent. And there are different movies people are imagined about different types of future. Like we have a totally virtual assistant. There's no embodied the body in the physical world. There are some evil robots. There were some very friendly robots and so on. So we can see that people want to build very intelligent things, maybe even smarter than ourselves. But the future is quite unpredictable. And this year, many people saying that even include giants like OpenAI, Anthropic, and so on. They say that this year is the year of AI agents. So we want to know, where are we? Where are we in the AI research today? We already have very powerful language models. We have very impressive reasoning capabilities from these models, but we also have limitations in the safety, the trustworthiness, multimodality capability of these models, the empathy, emotional support, embodiment capability, and so on. And also, we want to know what can be improved. What are the future directions? So we aim for this. We want to propose a unified framework to define the critical components and cycle of AI agents. We want to improve the lifelong learning capability, the complex reasoning, emotional grounding, multimodality, and so on, those key capabilities of a general agent. So based on this, we have a joint collaboration with around 20 institutions from the globe, and we conducted a very large-scale survey, as well as I would say it is also an opposition paper. We with the same title as our talk. It's also named as Advances and Challenges in Foundation Agents, and now it's in its version 2, which is much more comprehensive than its initial version. If you haven't read it, you can check that online. So let's recap the definition. So we say that an agent receives signal from the environment and making decisions about actions. But we don't know exactly this core component, how this cognitive process is defined, right? So this is the most exciting and mysterious part. So we want to have a framework to guide us about what to check, but how to design the framework. We can check our only model of true intelligence in the nature, our human brains, right? So if you compare the current AI agents with human brain, they have both pros and cons. So let's say some good words about our brains first. You can see that our brain is naturally strong in conduct continual learning, contextual learning, and AI agents, language models, they are relatively more data-driven. So now they're not task-specific, but still they require task-specific training data to improve its performance. And human brain is much more energy efficient, but this is not the case for LMs and other neural network models. And our brain is stronger in generalization, embodiment, memory, self-awareness, and like for agents, they are more relatively narrow and brittle, and they often disembodied or simulated, and they have more not so natural memories. They're more discrete. It's kind of like a storage system, requires strong retrieval and generation capability. And from until now, I still think LM and agents, they don't have awareness or true understanding. But like we said, so many good things about the biological brain, but it doesn't mean that LM and agents is not as good. So they have their own characteristics. They have their own unique strengths. So for example, they are strong in terms of the speed and precision. They can execute billions of operations per second, but our human brain is much more slower. And they have very large memory capacity, and they can be more accurate than us because they won't forget things, but humans can forget. And the scalability issue, they can scale as long as you give it more larger scale data and larger scale network model size, right? And also multitasking pluralism, access to external knowledge, no fatigue or emotion drift, those different characteristics. So basically what I want to say is that the best way to leading us to a more powerful and safe intelligence is not purely mimic the human brain, but to check the comparison in a critical manner and to find out the gap between human brain and AI brain and to see what can be improved, what is the unique strengths and weakness of each side. So we also conducted investigation about some critical characteristics, capability of human brain, and we found that we can generally categorize the development of different functionalities into 3 levels. We see L1, the green color is more well-developed capability. L2, the violet color is more partially developed or explored topics, and L3 is much more underexplored topics. So for example, language comprehension and production, as well as visual perception, they are very strong they are classified as L1 because we have conducted many years research about language models, natural language processing, computer vision, and those capabilities are quite mature and can be utilized in real-world products. And for many critical topics like the reward learning, planning, reasoning, semantic knowledge, understanding, and so on, they're also very hot research topics, but there's still significant space to keep improving them. And for L3, so for example, the episodic memory the cognitive capability, the working memory, global workspace, those series. We still have some research about it, but it's much less compared to other topics. But they're also very interesting and important characteristics of human intelligence. So basically, all we want to say is there's still a long way to go. And for this figure, note that the categorization of those is more subjective. We mainly want to show the gap between the human brain and intelligence, machine intelligence. So we can see that existing research about AI agents are fragmented and ad hoc. There are many different topics like planning, learning, workflow, like agent-to-agent protocols, and so on. So how we can form a unified framework for AI agents research. So these are some notations, but feel free, you don't need to remember those. We can directly check this framework figure. So basically, we defined a framework, what we call the foundation agent. If you check it from a high-level manner, it is consistent with what is defined in the Russell's AI textbook. So you also have sensors to perceive signal from the environment. You also have actuators to execute actions and have impact on the environment. What makes it more concrete is inside structure and process for the cognition part. So you can see, let's say we define what we call the agent loop from step 1 until step 6, and it recycles. So step 1 is, as usual, we perceive environment signals. We define it as ST, the state of environment at time step t. And then your sensor, which can be represented by a perception function, P, it turns the environment into an observation. And you can see it is not purely relies on the state of the environment, but also depends on what we call the mental state, so the MT-1. So what does this mean? It means that what you observed is not only depends on the external environment, but also depends on your internal mental state. So for example, in different circumstances, you may pay attention to different parts of the same observation. So which means that your attention will be guided by your current emotion, by your current status, right? So that's why this input observation is defined by both the environment and your internal mental state. So what exactly is what we call the mental state? So basically, we defined several core subcomponents to form a comprehensive mental state. So for example, the memory, so which is quite natural, it stores your past experience, it accumulates your prior information and help you to shape yourself. And the world model is more like it accumulates the information about the external world. And then it's like you have a more compact representation or modeling of the complex external environment. And based on it, you can reduce the time of trial and error. So for example, given a circumstance, you want to make some decisions, what action to take. Instead of actually try these actions one by one, you can utilize your world model to imagine, if I take action 1, what is the result? What is the future? If I take action 2, what is the potential output or the future, right? So world model helps you to better making decisions about the future without really try them out in the real world. And the reward, emotion, goal, those makes the agent be more active and goal-oriented. So also it helps turn the agent to be more human style, more emotional, and the reward keeps makes the model can keep learning from different types of inputs and feedback signals. So those are the critical components we identified for the mental state. And then we further define the cognitive process. So what exactly is the cognitive process? Basically, we define that taking your previous mental state, MT-1, and your previous action, AT-1, and your current observation of T, you update your mental state. So from MT-1 to MT, and you're making decisions about the current context. So you are making decisions about the action A of T. We can further decompose this cognition process into two phases, the learning phase and the reasoning phase. So what exactly is that learning? So in our framework, you can think that learning is the update to some long-term stuff. So basically, it's the update to your mental state, right? Because the mental state preserves all the information you had in your internal. So that's why we define learning as given the MT minus 1, A of t minus 1, and O of t, you get new M of t. And for reasoning is about more local information. So given the current context, the current decision to make, which action I should take. So we define a reasoning function R, and then it given the current mental state M of t, it will produce action sort A of t. And your sort of action needs to be executed to actually have impact to the external environment. So that's why you have an actor, which defined as function E. It will turn the action into executable action form and actually have impact to the environment. Then the state will update and the loop continues. So briefly speaking, like we define the core elements in the internal mental state, and we define the formal, we give the formal definition about the cognitive process, which involves learning and reasoning. So we have defined this framework, right? So what it can do, what we want it can do. So basically, our desire is that, so we define a foundation agent is an autonomous adaptive intelligence system designed to actively perceive the environment, continuously learn from experience, and reason about purposeful actions. So more briefly, like we hope that it is a fundamental intelligent unit with universal intelligent capability and can collaborate to form collective intelligence. So you can see we are actually like emphasize on two characteristics. The first is the universal intelligent capability. The second is collective intelligence, which means that like we hope that they can be formed, they can be grouped to form a multi-agent system and solve more complex tasks. That means that like if you think we can build a very powerful single agent to solve any tasks for us, maybe we can do it, maybe we cannot. But even if we can do that, it is not the most ideal way. Maybe it will require too much resource to accomplish this. Instead, like if you consider the human society, our human beings forms different levels of organization to tackle with more complex situations and tasks, right? I think that it can be reflected in agentic AI as well. So instead of build a very powerful single agent, a fundamental agent unit which can be formed to compose any organization structure is more realistic and efficient. So to accomplish such a fundamental intelligent unit, you must have some very basic capability like multimodal perception, cognitive adaptation, goal-directed reasoning, purposeful action, and multi-agent collaboration. And we also check that it has connection to other series, which means that it is consistent with many different existing series, but we're just considering things from a different perspective. So you can check the survey for more detailed discussion about these comparisons. Okay, until now, I have introduced the framework of foundation agents. Next, I will talk about two recent research we conducted this year. One is about reasoning and another is about memory. So what is reasoning? So as we have defined in the foundation agent framework, right? We define it as given the current mental state M of t, we infer the next action to take A of t. So biologically, like we say that human balance first intuition, which we call system 1, with deliberated analysis, which we call system 2. And from AI's perspective, so we want to combine the step-by-step, this very like deep reasoning process with parallel breadth reasoning. So it's like we want to explore different ways. So let's check some existing reasoning model. Let's say DeepSeek R1. This is a very popular figure from the Twitter, which shows the complex, like fully pre and post training process of the DeepSeek R1. So, but we can check a more high-level summarization. So basically, it shows that DeepSeek R1's training can be grossly split into 4 stages. The cold start stage, where the model begins with high-quality data and jump start examples, and the reasoning-oriented reinforcement learning stage, where we apply large-scale reinforcement learning training focused on reasoning tasks. And step 3 is the rejection sampling and supervised fine-tuning stage, where we generate new data, retaining high-quality outputs and fine-tunes. And finally, the final reinforcement learning stage, we apply reinforcement learning to improve helpfulness and harmonies. So we can see the reinforcement learning and chain of thought is being used extensively. So we can consider those things like chain of thought as depth-oriented measures. So let's say you have a standard prompt. Given the question, you ask the model to directly give the answer. But prior research have shown that this way it cannot solve very complex tasks. And if you instead of asking the model to give the answer, but also first output the reasoning process, how to solve the question step by step, you see in the middle part, the blue color text and the green color text are the intermediate steps to reason about the answer. And you can see with this reasoning process, originally the model cannot solve the question, but now it can solve it. There are other ways, for example, the self-refinement, which is asking the model keep refine its thinking process and produce the final answer. So those you can see it's increasing the depth of reasoning. So the pros is such kind of measures is interpretable and it contains step-by-step process which is explainable, but it can be slow and prone to error propagation. So if you make some errors in the middle, maybe it will lead to final incorrect answer. The more complex structured reasoning process, instead of you have a single chain, reasoning chain, on the left, you have the input, the output, and there are many intermediate steps. So you can generalize this linear style thinking process into more structured, organized manner, right? For example, you can explore several parallel chain of thought and find the output. And you can turn this multi-chain style into, let's say, tree style or directed acyclic graph style. So basically, with a more structured reasoning process, you have a higher chance to get a more optimal output. But also, it increases the cost of reasoning, right? So the process is more robust and reduce uncertainty, improves the answer quality, but cost is computationally intensive and requires pruning. There are many other LM agent reasoning approaches like model-based reasoning, test time scaling, planning with choice and memory. So we won't talk in detail here, but just want to show that there are different ways to improve the reasoning capability. So one paradigm is reasoning in the latent space. What it means is that instead of speak out the intermediate reasoning process, okay, let's do this by step 1 and step 2 and step 3. So the latent reasoning process is we don't produce the reasoning process. We don't decode this part. Instead, we just update the latent representation of the language model, and we update it for several steps. And these steps actually represents the reasoning process in the latent space. It's just we don't speak it out, right? So the good part is it makes the reasoning process differentiable, and also it avoids longer reasoning chains. So basically, it helps us to find a better reasoning process by automatic differentiation. So can language model adaptively combine fast heuristic and deep reasoning? So this is what we want to explore in this paper. So system 1.5 reasoning. So you can find this paper online. So we can see the problem of the current reasoning paradigms. The chain of thought reasoning improves model reasoning, but is often inefficient. So many steps don't actually contribute to solve the question, and models often overthinking. So let's take this example. Let's say we ask a very strong open source model, the QW 32 billion model. So what is the answer of 2 to 3? 2 plus 3. So even a child can directly tell you it's 5, right? But this model produced more than 900 tokens to answer this simple question. So you can see this is definitely an overthinking. So prior research, you can consider that there are different paradigms for prior approach. On the figure B, chain of thought is you have a multi-layer transformer, you reason about the intermediate steps, step 1, step 2, step 3. Those are intermediate tokens before you produce answer tokens. And for early exit, the image C, so you can see some blank block, which means that for each token during the decoding process, it's not always required to calculate many layers because, for example, some tokens may be quite easy to decode. Some tokens are more complex. So basically, early exit helps you to add an adaptive mechanism. So for example, when the token is easy to decode, maybe you just need 3 layers, 1 layers. When the token is hard to reason about, maybe you need more than 10 layers. So basically, this helps you to accelerate the inference. And compressed latent reasoning, as we described, is that it's reasoning in the latent space. And extra latent reasoning kind of combines the compressed latent reasoning with the explicit reasoning in the language space. Like in our work, we're trying to improve upon the prior research. So you can check from this figure. So basically, we combine the shortcut from the depth level to the time step level. What does this mean? It means that like, if you check those figures, each time after it decodes the current token, it will go back to the input layer. But now we're combining the shortcut from both the vertical direction and the horizontal direction. The idea is that first, for each step, maybe it can be decoded by various depths. This is explored in the early exit works. And the second is that if you think about when you calculate the latent representation at time step t, maybe you can have a very fast shortcut from the latent representation of time step t minus 1. So basically, instead of go to the input layer, we can have a fast track from the previous time step to the current time step at the same level, at the same depth, right? So that's why we call it adaptive latent space reasoning, because it's like you can freely traversal in any direction of the latent space. So how to train such a network? So if you think about it, previously, when you have a very regular transformer network, basically at each time step, you go from layer L minus 1 to layer L, finally to the top layer, and you go back to the next input layer. This is quite regular. But now it's like at each time step, you have 3 options. The first option is you continue with increasing the computational depth because you're not sure about what is the current token. The second option is you're already clear about the current token. You don't need to go further upward. But now you need to have more reasoning steps. So you go to horizontally to the right. And the third option is, okay, I already know the answer. I don't need to go upward. I don't need to have another reasoning step or horizontal step. Then I directly start decoding the answer. So as we have 3 options to take, which means we need a classification mechanism. This naturally tells us that we need to introduce a gating mechanism, right? So basically, we injected a gating mechanism at each step, at each layer, so that it can decide which path to go. And to train such a model, we combine 2 ideas. The first is about the teacher-student model. So we take a chain of thought reasoning model and take its latent representation as the teacher, and we let it to guide the latent representation of our model, which is reasoning in the latent space without decoding the reasoning tokens. And the second is how you can decide which step is we need more token, when we should go upward, when we should go right, when we should start decoding the answer. So basically, we utilized an existing algorithm called atomic thoughts to decompose question answering data into different steps. So if you think about the reasoning process of answering a question, it's like you can decompose the logic into some logical trees, and each root tree represents a critical step where we transit from a big step to the next step. And each leaf node is like a following reasoning step after those root nodes. So basically, we can consider those root nodes are like intensive reasoning nodes. Those leaf nodes are easier nodes. Then we can decide this time we should go upward, this time we should go right. So those two ideas helps us to solve the challenge of no labeled data and no like supervised signal. So because we learn the representation from a teacher model and we get the data from the data decomposition process. And this is the result we obtained. So basically we found that compared to prior reasoning models, we can achieve as good performance as original chain of thought, but we accelerated the performance by accelerated the speed by 20 to 55 times. And we only request 2 to 4 steps on these data sets. Question. But previously, those measures may require like more than 40 steps to answer some data sets. So basically, we found out like we can accelerate the reasoning process using our system 1.5 reasoning mechanism. And also, we have what we call the test time control. It means that like we have two values which we can adjust after the training the reasoning model. One is how many reasoning steps you want to take. So for example, let's say if you let the model to reason 2 steps in the latent space compared to reason 8 steps, definitely the later one will be more powerful, right? Because you take more computational time to reason about what is the output. And another threshold value, which is controlling like when I should continue go upward or when I should go horizontal or start decoding the answer. So as we can see, increasing any of these two values can increase the cost of reasoning. And in the meantime, you can improve the accuracy. So let's say if you already trained a reasoning model, then you are deploying this model into different tasks. For example, sometimes you're answering primary school level questions. Sometimes you're answering like graduate student level questions. Then you can adjust these two parameters without retraining the model. So to summarize, our system 1.5 reasoning dynamically allocate computational resource across both model layers and decoding steps. It enables efficient latent space reasoning and achieved high accuracy with very significant speed up. And in our future research, we want to integrate the memory and reasoning as a cognitive engine for broader agent applications. So next, we will introduce our research about memory. So first, you need to realize that actually the pure large language model, they are stateless, which means that if you give it input 1, it will produce output 1. If you give it input 2, it doesn't remember input 1. So it will give you output 2, purely depends on input 2. So this may not, this may be conflict with your impression about ChatGPT. But if you consider like how ChatGPT and other those chatbots works, basically at each time, it will append the previous dialogue history as a part of the new input. So it's quite natural that we want to attach a memory to maintain the history. So the external memory can make LM stateful. So for example, if you add a memory, that it can enable the continual dialogue, personalized agents, and long-horizon tasks. Because it helps you to store the historical information, right? And for human memory, like we have a hierarchy, different types of memory, like long-term, short-term memory, sensory memory, and we can further decompose long-term memory into more fine-grained types and so on. So basically, for human intelligence, the memory also helps to store experience and knowledge and support learning, reasoning, and planning, enables identity, imagination, and adaptation. So basically, like from different disciplines, people all think memory is the core part of human intelligence. So we categorize the memory's main research question into representation and life cycle. So for representation, like how we define short-term, long-term sensory memories. For life cycle, how the memory system starts from acquisition of the raw sensory data to encoding it into meaningful representation and derivation to drive useful information and get rid of noises. And retrieval is like when you need to retrieve the relevant information, how you efficiently retrieve the most useful part. And utilization is that given this information, how exactly you are going to use this memory information to improve your generation. So this shows the different types of memory and the corresponding techniques. So basically, for sensory memory, it means the initial encoding and transition and retention of the sensory input. The short-term memory means the temporal storage for immediate task-relevant data, and long-term memory means the durable information storage, so enabling knowledge generalization. And we listed like some typical examples here, and you can check the paper for more details. And for life cycle, as we explained that like the acquisition is capture the signal from the environment, the encoding is transform the sensory input into structured internal representation. Derivation is about extract valuable insight, refine the stored knowledge. Retrieval is about efficiently locate the useful information from the memory system. And utilization is like how retrieved memory are applied based on reasoning, planning, creativity, and so on. And we can categorize memory into two types, the external or explicit type. So basically it means that you can store your memory into a storage system. For example, relational database, vector database, graph database, and so on. So it's quite clear that if you store information in a database, it is easily editable and interpretable. You can store as much information as you want. But also it requires a retrieval process. It introduces extra latency and the storage cost. Another way is implicit. So basically, you learn the data and you encode information in your model ways. So, or you can call it internal memory. So the information is encoded in model ways. It's always available. There's zero latency, but it's also hard to update and audit. For example, if you want to revise an information in a model weight compared to revise the information in a database, it is more difficult and takes time and technique to like accurately locate the information, and you also need to ensure whether this edit won't impact other informations, right? This is more complicated. So this is what we call the retention and the retrieval trade-off. Like with external database, it's easier for retention, preserve the original information, but it introduces cost for retrieval. And if you have an implicit model to store the information, you don't have retrieval cost, but the information retained in the model weight may be not as accurate. So our objective is to improve the implicit memory, improve its information retention, and also reduce its retrieval, improve the retrieval accuracy. We want to maximize both the retention and the retrieval. So how can we do this? How can we simultaneously maximize the retention and the retrieval while keeping the external storage minimum? So this is based on our recent work, which we call the R3MEM, bridging memory retention and retrieval via reversal compression. You can also check this paper online. So we call it generative memory. It means that like, if you instead of think about a memory as a like storage system, like you store some information, if you input a query, it will output a matched text. So instead, we can consider the memory itself is a generative model. So for example, you have language model, which plays the role of memory. So the advantage is that such a generative memory keeps talking with the user. It will better understand the user and can give the most personalized, useful, suitable result. So for example, traditionally, if you do retrieval, you will have the process of query rewriting, right? But if you have a generative model, basically, if you give it a query, it will understand the query from its internal computational process. You don't need to explicitly conduct a query rewriting. And then it will generate the answer instead of retrieve the answer. So basically, if you compare it with a search engine, it's like on the left is a personalized assistant, which knows you the best. On the right, it is on average, like the best performing search engine, which can give you a quite classical result, but maybe it's not the best for this specific user. So to build what we call the R3 we combine with several ideas. The first idea is that we consider memory as the compression process. So it's like the retention is, you have the original context, you compress this long context into a more compact representation. This is what we call the memory. And for retrieval, it's like you give a query. Based on this query, you can decompress the original context. So then this naturally forms a dual task. It is a reversible process, right? You have the context, you get the memory. You have the query, which represents the compact memory, you get the context. So to easily achieve such a dual process, we want to have a reversible memory network. So basically, this is related to the research about reversible neural network, which means given the input X, you calculate Y. And given the input Y, you can reverse back the original X. So you can see that it is achieved by defining two modules, F and G. And if you define the calculation of X and Y using this auxiliary F and G module, you can define such a reversible calculation process. As for transformers, they're not reversible, but you can mimic this reversible neural network by introducing an F and G adapter. So it's similar to the previous image, but now after you introduced such two adapters, you can fine-tune the model without change the original language model's ways. So for example, you fix the original language model, but you only do LoRa to this adapter part, then you can improve this model and turn it into approximately reversible network structure. And the last idea is about what kind of data we can have to train such a model, right? So it's not always easy to get large amount of high quality data for memory training. But consider our viewpoint of compression and decompression. Actually, we can construct such data automatically using an AI, for example, ChatGPT-4. So the idea is that you can collect a set of high quality documents, and you can summarize this document into paragraph level, into sentence level, and finally into entity level. Then this forms the different granularity from the full document to paragraph, sentence, and entity. And then you can construct different pairs at different layer. So using paragraph as query, you get the document. Using sentence as query, you get the paragraph. So combining all of this, we get the R3 architecture. You have the automatically constructed multi-granularity compression data. You have this reversible transformer as the backbone of your memory network. And we also introduced what we call the virtual memory token, which is similar to the CLS token of BERT model. Basically, this virtual memory token helps to compress the information from the longer granularity to generate the shorter ones. And we can use this pairwise data, from long to generate short, and from short to generate long, which means given the context, you generate the paragraph. Given the paragraph, you reverse back the full document and so on. And this is the training loss. We combines the forward generation loss, backward generation loss, and the consistency loss, which is compare the recovered text with your original text. And these are the experiments. So basically, we have the best retention performance compared to the different baselines when we submit the paper. And we also have the best retrieval performance compared to many retrieval algorithms. And lastly, we also consider this memory component as a single memory module, and we're plugging it into an agentic framework. And compared to many other popular memory framework at that time. So for example, we compared with memory bank, memory rack, and we show that in terms of different criteria, like the contextual coherence, ranking score, retrieval accuracy, response correctness, and the overall metric. In terms of all these different metrics, we perform the best. And our application study shows both the hierarchical compression data, the virtual token, and the reversible architecture contributes to the final performance. So to summarize, our RCMM frame memory as a reversible compression problem, and we defined this RCMM, which is an adapter-based reversible transformer with virtual tokens, and achieved the best performance at that time. So next, we want to integrate the human-like memory dynamics into AI system for more powerful and reliable performance. So lastly, I want to quickly introduce our application research about applying AI agents for material science. So basically for material generation. So this part is based on our submitted paper named Accelerated Inorganic Material Design with Generative AI Agents. It's a collaboration between Mila and the Tokyo University. So basically, the design of inorganic crystalline material with specific property is very crucial for different techniques. For example, we want to have structural material for buildings. We want to have energy material, functional material, and sustainable materials. There are different types. So the general process is like you have some desired property, and based on this desired property, you have a generative modeling process to produce the candidate material structure. And given this material structure, you can utilize what we call the density function theory simulation, DFT simulation, to predict the property of this structure. And you can see whether the property of the generated structure merges with your target properties. If it's good, then you have your result. If it doesn't merge, you have some feedback, and you can continue this loop. So previously, people used diffusion models for inorganic material design and actually also for other types of material. So basically, the idea is you can represent the crystal structure with its lattice vector, atomic coordinates, atomic species, and so on. So basically, you have a way to represent the structure of a crystal material. And then you define it as a diffusion process. The property is your guidance, right? It helps you to decode the crystal structure using this numerical representation. Another way is use language model. Basically, language model can help reason with its knowledge learned from large-scale data and directly output the structure in CRF format, which is a specific way to represent the structure of materials. But there are some limitations. So first is that for these algorithms, it's still hard to precisely meet the target property, and the exploration is limited by the pre-trained knowledge in the language models, and there are poor interpretability. So how we can further improve upon these two paradigms? So how can we achieve a framework that can explore broader material space in a self-driving way with sufficient interpretability? This is what we want to ask. So we have several ideas. The first idea is that we want to navigate material space through the iterative refinement. Instead of giving the input property and generate the structure, we want to have a iterative process. This is quite natural. We want to get feedback from the previous generation and better improve in the next iteration. So how we can explore material space in a self-driving way with sufficient interpretability? The second idea is we want to use a language model as a central reasoning engine. So instead of only use LM or diffusion, we decompose this process into a planning and generation process. So basically, we consider that the language model is more powerful in generating a step-by-step plan about how we can design the structure, what kind of elements, what kind of structure we should use in the final output. Then based on the produced natural language guidance, we have a diffusion generation model to diffuse the structure based on the input guidance. Then the step 3 is we want to further reasoning like a human expert. So instead of only use a language model, we want to turn it into an agentic system. So by providing it with many external resources like short-term memory, which remembers the recent proposal and feedback. The long-term memory records past successful trials and reasoning. The periodic table, which suggests chemically related elements and knowledge base, provide insight from non-composition property relationships. So this gives our final framework. So you can see we have 4 stage, which is a iterative process. The stage 1 is given the property, we conduct a LM-driven planning. So it will select appropriate tools and think about the structure and give a candidate output. The step 2 is LM-driven proposition. It will, based on the feedback, it will propose a composition structure. And step 3 is you have a diffusion model to generate the crystal structure. And step 4 is you have a graph neural network as a predictor to evaluate the property of the generated material and prepare the feedback. And based on the feedback, you continue with this loop. So this shows the detailed process of the stage 1 planning. So basically, you can see the prompt is that, okay, you tell the language model, your objective is to propose some material based on some criteria. And it is also given a to-do list, the tool list, the short-term memory, long-term memory, periodic table, knowledge base, and so on. And it also have the planning history. It knows what it has already done in the previous iterations. Then it will retrieve the relevant useful tools and go to the next step. Stage 2 is LM-driven proposition. So for example, in this image, it selected the short-term memory. So the prompt for language model is that based on the above information, write a reflection on your previous suggestion. So the model will think about like what is good in the previous part and what is bad. And it will conduct more in-depth reflection about the previous generation results to help improve this round of generation. Then step 3 is after the language model produced a new output, the diffusion model will take this composition instruction as input and produce the final 3D structure representation. And lastly, we have a graph neural network to take the generated candidate structure and predict the property. And based on this property, you can have a feedback, whether this value is higher or lower than the desired property values, right? So this forms the final, the whole iterative process. And let me show the experimental result. Let me be quick. So basically, we tested different experimental setups with both different target values. So what we found is that, so for example, the tool selection pattern will vary according to the task difficulty. So for example, for low formation energy target, the language model frequently use knowledge base and long-term memory. And for high formation energy target, it will increase the use of periodic tables. So basically, it means that the language models exhibit adaptive to selection behavior depending on the task difficulty. And the second is that we found that like the LMs can dynamically adapt its strategy based on the result from the previous iteration. So this is based on our further analysis by analyze each run into early stage, mid stage, and late stage. So you have different iterations. The first 5 iterations is the early stage. The intermediate 5 iterations is the intermediate stage, and the last 5 iteration is the late stage. And we can see in different stages, the use of different type of tools is changing. And also the success rate over iteration is also improving, which is matches our expectation. And high success rate is not enough. We also want to evaluate the validity, the novelty, and the diversity of the suggested materials. So we have different metrics to measure. And this is our result. So basically, we found that the tool-assisted math agent can significantly improve the uniqueness and novelty. So the validity, the novelty, and the uniqueness, all these different metrics are measured and compared with other methods. Also, actually, we can control what kind of elements to include or exclude in the generated crystal structure. So basically, like what we found is that the math agent offers built-in interpretability. It provides reasoning for each suggested composition in natural language, and it helps human experts interpret the materials design process and potentially expand the domain of knowledge. So here we show that like we can actually ask the model to replace the element with some other specific element in this crystal structure. And actually, the model can follow the guidance from human expert. So this shows an example of avoiding some elements in the output, and this instruction is successfully executed by the math agent. So to summarize, the motivation is that we want to design inorganic material with target property, and the existing method struggle with limited interpretability, low precision, and lack of autonomous exploration capability. And for our proposed math agent, it is a generative framework for material design powered by LM-based agents and enhanced by this iterative generation process. So the key findings are like we can successfully explore towards target properties with a high success rate, and it generates material valid and diverse by integrating different tools. And also the reasoning behind each proposal is provided, allowing researchers to understand the process. So basically it provides explainability to the generation process and handles real-world constraints in plain language with high fidelity. And these are about future source. So basically, this is the link to the paper and code. So if you are interested, you can contact the first order student. So as we can see that language models and LM agents are become more and more powerful. So, but there are still many research questions which are very interesting and challenging to tackle with. So to conduct more broad and in-depth research about LM agents, so we started organization named Foundation Agents, where we are collaborating with different researchers around the globe to conduct research about AI agents. For example, we are working on different open source agent frameworks and also agent protocols. So if you want to join this organization, you can check this website. And also, these are the links to the Twitter, GitHub, and registration form. So yeah, thank you. These are all the contents of today.
Okay, thank you, Professor Liu, for the inspiring talk. We're now open the floor for questions from the audience. So please drop your questions in the live chat. So the first question we have here is, in practical applications, how does R3 avoid issues like information drift or false recall in its memory mechanism?
So I won't say that R3 can fully avoid the information drift. So basically, the core contribution in R3 is how we can model the memory component as a generative model. So for example, how we can utilize an existing Llama model or any other open source language model and turn it into a memory network. And we further identify the core capability, which is about the information compression and information retrieval. And we automatically design those data to turn it into a memory network. And for information drifting, so I think it's a problem of continual learning and catastrophic forgetting and so on. So I wouldn't say RCMM is able to avoid such a problem.
Okay. Let's see. The next question is, um, does R3 rely on a specific type of vector storage or indexing structure?
No, it doesn't rely on the choice of vector storage. So basically, like previously, people often ask me, this means that the latent memory is better than external memory? I would say no. So for example, let's say if you think about what kind of information should be memorized by your brain. So I would say if the information is more like important knowledge, it is valuable to be memorized and stored in the model weight or in your brain. But if the information is just some detailed information with not a long-term value, for example, it's a detailed table of some humans, so maybe you just want to check it when you really need it, then this such kind of information should be stored outside. And this is like more subject to the situation of the agent. So for example, let's say if an agent is your personal assistant, then many details about this specific user should be remembered. But if an agent is like open to all the public, it is not supposed to remember the details of each single user. Instead, it aims to like provide the best service like for all the users. So basically, it means that like first, the vector database is more for the explicit external storage. It's not for this RCMM implicit memory. And the second is we can combine this implicit and explicit memory. And like it is not saying this one is better than that or that one is better than this. They are suitable for different circumstances.
Okay. Next question. In the design of math expert and math agent, how does AI complement human experts?
I would say like this is actually not limited to material science, right? How AI complements human expert. So you can see that human expert can guide the model to more efficiently explore the large space. And let's say a human expert, it, the expert cannot remember all the materials, remember all the literature, but the agent can search a very large space. And also, like the human expert cannot like understand every like single paper, every discipline, but the model can accumulate very broad range knowledge. So I think they complement with each other. The AI part is more scalable. It has very broad like knowledge, but it may be lost in the very large space. The human expert have very deep insight, have strong reasoning capability. It can guide the model to first converge into a optimal zone. So that like by combining human expert and AI to form a human in the loop paradigm, I think it combines the best part of both worlds.
Okay, thank you. I think that brings us to the end of today's lecture. Huge thanks again to Professor Liu for sharing his expertise on foundation agents. And we'll share the replay and slides through our community channels. So don't forget to follow us on socials, join the Discord and Telegram groups. Stay tuned for the upcoming episode. See you.
Thank you. See you.